Welcome to lecture number 30 of the Statistical Thermodynamics course. So we have already in the previous lectures covered what is called a transition dipole moment. And we also saw that if M12, which is the transition dipole moment, is zero, that transition between two rotational, vibrational, and electronic states is impossible. A spectral line only, emerges when its transition dipole moment is non-zero. Okay, and usually the more intense lines in the spectrum arises when Mij, which is the transition dipole moment, is higher. Okay, so this we already covered in the previous class, in the previous lectures. So this time we are going to look at some of the, when we look at all these things, that you can see that it is actually an onerous task to determine the transition dipole moment. But however, fortunately, determining the selection rules, the selection rules do not actually require evaluation of all possible transition dipole moments. So this is good news, all transition dipole moments. Indeed, if you look at the mathematical symmetry of a wave function, okay, it is defined through its quantum numbers so that you can distinguish between the zero and the non-zero values. This can be usually done by inspection. Okay, so the primary selection rules can be expressed, okay, quite simply in terms of the allowed change in characteristics quantum numbers. So therefore, the primary selection rules, okay, can be expressed okay, in terms of allowed changes in characteristic quantum numbers. Okay, characteristic quantum numbers. So we already have seen, for example, in the book, table 6.9 lists all the selection rules that can be derived. Okay, so the selection rule, let us look at the selection rules. So the selection rule for the rigid rotor, delta J is plus minus 1. Okay, so this comes from the mathematical properties of spherical harmonics. Okay, since the spherical harmonics depend, you know that the spherical harmonics depend on theta and phi. Okay, the rotational, this implies that the rotational transitions can occur for molecules okay, having a permanent dipole moment. Which in other words means mu is not equal to 0. Okay, so if you look at this now, the permanent dipole moments or the non-zero dipole moments are impossible for molecules endowed with spatial symmetry. So non-zero dipole moment, because it will cancel out, dipole moment, okay, is impossible, okay, for molecules, okay, endowed with spatial symmetry. Okay, so for this reason, precisely because of this reason, okay, the homonuclear diatomics, okay, are forbidden, from undergoing rotational transition. Transitions. All right. Okay. So homonuclear diatomics are actually forbidden from undergoing rotational transitions. Non-zero dipole moment is essential for rotational transitions, but because of the spatial symmetry, the homonuclear diatomics cannot undergo this kind of transitions. Okay. So now in a similar fashion, okay, selection rule for harmonic oscillator, okay, gives plus minus 1. Okay, this depends on the mathematical properties now. Okay, of the Hermite polynomial. Interesting. So this depends on the mathematical properties of the Hermite polynomial. For such polynomials, if you want to evaluate Mij, it requires, so if you want to, for this kind of polynomials, if Mij needs to be evaluated, then what you do is basically you expand a Taylor series expansion of the dipole moment, okay, about the equilibrium nuclear separation. So this requires a Taylor series expansion, a Taylor series expansion of the dipole moment, about equilibrium nuclear distance. Okay, because remember the harmonic oscillator was only true for very small magnitude of oscillations. It's very near, it's the most potential actually. The harmonic oscillator was only valid for a very small distance, internuclear distance. Okay, so if we follow this procedure, we find, so vibrational transition mandates, okay, spatial variation in the electric dipole moment, which means du mu by dr cannot be equal to 0. Okay, so this is what is required because all homonuclear diatomics have 0 dipole moments. So all homonuclear diatomics, okay, have 0 dipole moments. Okay, this translates to forbidden forbidden vibrational as well as rotational positions. Okay, so employing this calculated dipole moments and measured spectral signatures. So what did spectroscopists do is that the calculated dipole moments plus the measured spectral signatures. Okay. Okay. We found that the electronic selection rules, electronic selection rules can be based solely, okay, in terms of the term symbols, in terms of the term symbols related with the energy levels, related with the energy levels, okay, associated with the energy levels involved in any electronic transition. All right. Okay. So so let's look at it for atomic spectra. For atomic spectra, okay, the generic term symbol and associated primary selection rules. Are 2s plus 1 Lj delta j 0 plus minus 1 delta L plus minus 1 delta S is equal to 0. But note, delta J equal to 0 is forbidden. Okay, if both electronic levels okay, correspond to J equal to 0 states. Correct? Okay. Moreover, delta J rule is mandatory. Okay. Delta L and delta S rules become less so. So for Z greater than 40. Okay. Now let us look at the diatomic spectra. Okay. So here the generic term symbol and primary selection rules are 2s plus 1 0 minus 1 delta S is equal to 0. Okay. Selection rules when needed are as follows. Selection rules are follows. Zero plus or what not. Homonuclear diatomics. Okay. So if you look at this particular equation now, let's call this one. Okay. And we note that, now let us perhaps do table 6. If you look at table 6.8 very quickly, let's go to table 6.8. 6.7. Let's go to table 6.8. So if you recall that electronic energy levels for O2, say for example, where the term symbol was X3 G minus TE, this is the term. T was 0, and then you have G electronic. This is the degeneracy, effective degeneracy was 3. Then you had A 1, G, so 7, 9, 1, 8 or so, 2. So similarly, then there B1. This is just a recap so that you get the idea. 13195.1, 1. And then there is A3 U plus A3 5 and 397.8 3. And then there is B3 minus U, which is 49793.3, and this is 3. Okay, so this was the oxygen electronic energy levels of oxygen, which we already know. Now this was already done, and then if you look at the figure, which is for oxygen, if you recall this figure once again, it's basically figure 6.10 from the text, where basically the same energy levels were represented in a pictorial fashion, if you recall. So if you take both of those two things into consideration, this table and the corresponding figure, which is drawn in the form of a potential well, okay, you will find that, okay, that most transitions from the ground to the upper electronic states of oxygen are forbidden. The only allowed transitions for oxygen corresponds to Schumann and Runge systems, which would mean B3 U minus to X3 minus, okay, which accounts for this. Basically, what does it do? It accounts for absorption of UV light at wavelengths below 200 nanometer in the Earth's atmosphere. Okay. So given this electronic transition for oxygen, we realize that the permanent dipole moment is unnecessary for homonuclear diatomics. The general conclusion is significant. First, as it might be expected, that the shifts between electronic orbitals, the transition dipole moment depends preferentially on the portion of the dipole moment established by the electrons and not so by the two nuclei. Second, because their rotational and vibrational transitions are inherently forbidden, access to molecular properties is only possible through electronic spectroscopy. So since homonuclear, since rotational and vibrational transitions, okay, are inherently forbidden. Okay, access to molecular properties. Okay, of homonuclear diatomics. Okay, is only possible through electronic spectroscopy. Okay, so through electronic spectroscopy is the only way in which you can access those levels. Okay, so let us also write the selection rules in a more most compact form, so that you have an idea of where to look up. So this is primary okay, selection rules for rotational, vibrational, and electronic energy modes. So if we look at the table now, this is the energy modes. This is the model that correspondingly it does, and then the selection rules. Okay, so there is first is rotation. So the model is a rigid rotor, and the selection rule is delta J is equal to plus minus 1. Then of course the model is vibration. Okay, this is called a harmonic oscillator. So the most potential is the more apt description, but it is valid for low amplitude oscillation. So this is plus minus 1. Then of course electronic for atoms is 2. For atoms it is 2s plus 1 j. Okay, so here the selection rule is delta J equal to 0 plus minus 1. Out of that we know what is forbidden, and delta L is equal to plus minus 1, delta S is equal to 0. Okay, then of course electronic, and this is the last one, this is for molecules. Okay, 2s plus 1, this plus minus 1, delta S is equal to. Okay, so these are the different modes. Okay, and evaluation, and we remember that Mij is called the transition dipole moment. If this is equal to 0, then you see those transitions are not possible in the first place. Okay, so now we have got a very good idea about what are the different energy levels, what is a transition dipole moment, how the transition dipole moment can be evaluated from a perturbed version of the time-dependent Schrodinger's wave equation, and what are the corresponding rotational and electronic transitions that are possible for homonuclear diatomics, which is only electronic spectroscopy or electronic transitions that you can access, not any other transitions. Okay, and the selection rules are given in this particular table that I just did. For rotation, okay, it is rigid rotor, you have this vibration harmonic oscillator, and for the electronic you have this bouquet, depending on whether it's an atom or a atomic molecule. These are the kind of rules that we prescribe. So in the next class, what we are going to do, we are going to go into the spectroscopy of diatomic molecules, and we are going to present a quantum mechanical analysis of the internal energy modes and see that how these energy modes can be used to find out what are the different spectroscopic possibilities. Okay, so till then we go for the next lecture. This lecture is concluded herewith.